So let's start. Do you have any questions? Any questions on chapter 4?
يعطيك العافية. خير.
Sorry, can you repeat, Mina? Any questions?
دكتور أنا سألت ما بعرف إذا
ما سمعتش أنا كان
لا يعني لسه ما سألت سؤال. دكتور أنا عندي بس سؤال صغير عن الواجب اللي نزل لشابتر 4.
نعم.
وبس أول سؤال مطلوب منا إنه نعمل functions ونسوي السيركت تاعتها اللي بتطبق هاي الفانكشنز، ومحطوط لنا إنه نستخدم the minimum number of NAND gates.
أوكي.
يعني بس نستخدم NAND gates ولا نقدر نستخدم other gates ولا بس NAND gates؟
لا، بما إنه the minimum number of NAND gates, then you have to use NAND gates with the minimum number.
Alright, أوكي تمام.
Okay, بس.
لا بس هو هيك عشان ما فهمت كثير السؤال يعني.
So you need to use NAND gates only, and you have to use the minimum number of NAND gates.
Alright, doctor, thank you.
Okay.
Yeah.
Other questions?
دكتور سؤال.
تفضلي.
بالناند جيتس ايش اكتر انبوت ممكن استعمله؟
ما حدد لك.
اوكي يعني في 5 مثلا.
في
5 input NAND gate.
يس بس هي implied انه جواها يعني في نتز جيتس اصغر.
اوكي.
تمام. All right. So last time we finished chapter 4, where we talked about the design and analysis of combinational logic circuits. We saw how to analyze a combinational logic circuit. We saw how to design a logic circuit, a combinational logic circuit. Then we took a few examples on some of the common combinational logic circuits that you usually see in or use in digital, the design of digital logic systems, such as adders, subtractors, decoders, encoders, multiplexers, demultiplexers, and there were two more examples on the slides, which were the magnitude comparator and the BCD adder. We may come to them by the end of the semester as examples, as design examples if we have time, but you can easily look at them on the slides, what is meant by magnitude comparator and how to design the magnitude comparator. At the end of the day, they are combinational logic circuits, but if you look at them, you will see that they are not designed using the straightforward approach or the conventional approach, which relies on using a truth table and simplification and all that stuff. Basically, for example, the magnitude comparator, it is designed based on our understanding on how we compare the magnitudes of two numbers. So if you have time, look at the magnitude comparator. It's a nice example. It gives you another perspective on how to design some logic circuits other than using truth tables and key maps and all that stuff. Okay, so I will come to it if we have time or if we hold some office hour later to discuss the magnitude comparator. Okay, so that was all about what we need to know about the combinational logic circuits. And we said at the beginning of chapter 4 that combinational logic circuits are one example of logic circuits. It is one type of logic circuits. And there are other types of logic circuits. And this is basically our topic for the rest of the lectures in this semester. We will discuss a new type of logic circuits, and I will use the slides for this chapter and the remaining chapters. I will use the slides, but I will still use the board in many occasions and for additional examples. But in order to save some time or the time that I spend on writing on the board, the text and definitions and all that stuff, I will use the slides to save some time, but I'll still use the board to do some examples. So I will share the slides with you, and these slides are basically a modified version of the slides that are already available on e-learning. And I will post them by the end of this week, because I'm modifying them. I'm adding additional details and additional examples. So I have not finished editing them, but once I finish them, I will post them on e-learning, but in the virtual classroom section. I will not add them to the slides section. I will add them to the virtual classroom section in order for you to know that this is the set of slides that I'm using. So let me share the screen, which is this. Okay, so now you see my screen, I assume. Right, so everybody sees the slides, I assume. Okay. All right, so our next topic is basically from chapter 5, where we, as I said, we will discuss a new type of logic circuits, which is the sequential logic circuits. Chapter 4 was all about combinational logic circuits. Now we will talk about the sequential logic circuit, and specifically we will talk about one type of sequential logic circuit, which is the synchronous sequential logic circuits. So there are many types of, there are two types effectively of sequential logic circuits, the synchronous and the some other type that we'll see shortly. And in chapter 5 and in this course, we only consider one type of sequential logic, which is the synchronous one. So okay, so as I said last time, when we last time we finished chapter 4. We finished chapter 4, in which we talked about combinational logic circuits. And if you remember, when we started talking about combinational logic circuits, we said basically that combinational logic circuits are those circuits in which we have certain number of inputs and certain number of outputs. In this diagram, we have n inputs and we have m outputs. And we said that each of these outputs is basically a function of the input value only, or it is a function of the input combination, the current combination that appears on the input. So whatever value we feed to this circuit, this value is transformed, is manipulated by the circuit, is modified by the circuit, is used by the circuit to compute the output value or values, depending on the number of outputs of the circuit. So this is very straightforward and at the same time, it's very important, because this is the distinguishing factor between the combinational logic and the sequential logic. So in the combinational logic, basically, we have n inputs, we have m outputs, and any of the outputs is basically expressed as a function of the inputs, of the input value that appears at the input, or the input combination. And that's why these circuits are called combinational logic circuits, because they rely only on the input combination to compute the output value. So this type of circuit was very useful. We used it to design many circuits for different purposes, for different applications, such as those we designed in chapter 4. In chapter 4, we started by designing circuits that can compare two numbers, circuits that look at the input, investigate the input, and output some value based on some conditions. We designed the decoder, the encoder, the mux, the adder, and all these examples. So this type of circuit is very useful. It is widely used in the design of digital system. However, these circuits might not be always useful. These circuits, sometimes the required system, the system that is to be designed is supposed to do something that cannot be achieved by combinational logic circuits. For example, if we consider the design of a circuit or a digital system that is capable of counting from 0 to 9, and incrementing the count is basically based on some external input, such as a switch. Whenever you push the switch, the count value is incremented by 1. Suppose that you want to design such a circuit where there is an input which is connected to a switch, let's say, and whenever you press that switch, the count value is incremented by 1. So the circuit should start by from 0, and when you press the switch the first time, the count value is incremented by 1 to 1. You press the switch one more time, you move to 2, you press the switch another time, the count value becomes a 3, and so on. So basically, if I ask you, how many inputs does this circuit have? You will say there is only one input which controls when to increment the count value. And how many outputs will you have, assuming that you want to output the count value, which is 0, 1, 2, 3. How many outputs you will have? 10. How about 4? We are talking about a digital system. So we need to represent the output, which is basically the numbers from 0 to 9 using binary. Everything is binary. So how many bits you need to represent the values from 0 to 9? You need 4, exactly, which is a BC, like BCD, right? So so basically, if we want to design a circuit such that there is only one input and there are 4 outputs, let's say this is input X, this is output, let's say Y3, Y2, Y1, Y0, such that whenever there is a 1 on the input, the output value is incremented by 1. So this is what we call a counter circuit, or a circuit that can count. And it counts through a certain pattern. And in our case, it counts from 0 to 9. And when it reaches 9, it goes back to 0 and so on. And the control or the counting process is controlled by this input. So the question is, given this understanding of our circuit, and as we said in chapter 4, in order to design the circuit, we need to understand the circuit. We need to understand the circuit in order to be able to determine the number of inputs, the number of outputs, and the relation between the inputs and the outputs. So we know now the number of inputs, the number of outputs, and we know what is the relation between the input and the output, which is whenever the input is 1, increment the output by 1. So can we design such a circuit based on the combinational logic, based on combinational logic circuits? What do I need? Just think about it. I know that there is one input, there are 4 outputs, and I know the relation between them. Let's assume that initially the output is 0, 0, 0, 0, and the input becomes 1. What should the output become after when the input is 1? It should become 1. And if the output is 1 and the input is 1, then I have to increment the output by 1. Now, if you look at the operation of this circuit, there is something that cannot be done by combinational logic circuits. What is this something?
دكتور
Yes.
إنه يحفظ القيمة اللي قبل.
Exactly. Thank you. Exactly. Now, if I want to count based on the input. Then in order to know the next count value or the new count value, I need to know whether X is 1 or not. And at the same time, I need to know what is the previous count or what is the current count. So I need to know that I have reached to count 3, for example, so that whenever X becomes 1, I can increment Y. But in order to increment Y, I need to know what is the current value of Y, which is a 3. So when I see that X is 1, I increment 3 to become 4. And when X becomes 1 again, then I need to increment Y. And what is the current Y? Now, currently Y is 4, so I increment it, it becomes 5, and so on. So there is very important thing here. Combinational logic circuits cannot work in this example. Cannot work because we need to memorize, we need to remember what is the current count in order to determine what is the new count when X becomes 1. So this is very important. This is the attribute, or this is the feature that distinguishes combinational logic circuits from the new type of circuit, which is the sequential logic circuit. Okay, so combinational logic circuits will not work, will not be useful if we want to design this counter. Will not be useful if we want to design this counter circuit, which counts from 0 to 9, and any other circuit that have the similar behavior, which is what are these circuits? What behavior I'm talking about? This behavior is basically the output of the circuit does not only depend on the input value, on the current input combination or the current input value, it also depends on something else. What is this something else? It is the value that I am memorizing, the value that I have to store, the value that I have to remember in order to compute the new output. And this value is very important. The value that I need to remember is very important. It defines the state of my circuit, the state of my system, okay? And this state is now used, I have to memorize, and at the same time, I have to use it to compute the new output along with the input, okay? So basically, in order to design this counter, typing on the, to design this counter circuit, basically we need to add another component to this combinational logic circuit, which is basically a component that can memorize. And in this example, what is the thing that I want to memorize? Basically the current count value, right? This is the current count value. So now, based on the current count value and the current input, I can calculate the next count value, right? So this is basically what we are going to discuss in this chapter, which is basically a new type of circuits, which is called the sequential logic circuits, which are basically combinational logic circuits. Nothing is new, and you will see later in 2 or 3 lectures that sequential circuits are combinational logic circuits. However, they come with additional component, which is the memory or the storage, the memory or storage. We need a component, or we need a sub-circuit or a new circuit that can memorize. And this is the first topic that we will cover in this chapter, which is basically how can we store data? How can we store 2 bits, 1 bit, 3 bits? So we'll talk about what we call the storage elements, how to store the bits. Now, what is the differentiating feature between the sequential logic circuits and the combinational logic circuits? We already talked about this. We said that the output in sequential logic circuit is dependent not only on the input, but also on the stored value or the remembered value, or basically we like this term, which is called the state, حالة الcircuit, مظبوط. This is the state of the circuit. حالة السيركت. What is the circuit remembering? What is the value that is stored in this circuit? And whenever you get confused, always remember our previous example, the counter. What do you need to implement such a circuit? You need to know if the input is 1, and you need to know what is the current value or the current count value, which we call the current state or the present state. الحالة الحالية. What is the circuit remembering now? So this is called the state, or technically the present state. So this is the difference between sequential logic and combinational logic. Sequential logic is technically combinational logic and or plus memory. So in this chapter, we will study how to analyze and design sequential logic circuits. How to design and analyze sequential logic circuits. And these circuits are very, very important in digital systems. Almost every digital system has some form of sequential logic circuit, have some form of sequential logic behavior, let's say. Okay, now there are basically two types of sequential logic circuits. Some of these sequential circuits are called asynchronous sequential circuits, and the other is called synchronous sequential circuits. In this chapter, we will consider this synchronous type. The asynchronous type is not widely used because it is complex to design, and it is usually discussed in advanced logic courses. However, let's look at the difference between the asynchronous and synchronous sequential logic circuits. So for the asynchronous sequential logic circuits, the block diagram is basically a combinational logic circuit. So it is a sequential logic circuit. So it has a combinational logic component or a combinational logic circuits. It has a certain number of inputs, certain number of outputs, combinational logic circuit. However, since it is a sequential circuit, then it should have a memory element or memory storage. It should have some circuit that can memorize, which is the storage elements or the memory. So now, based on the value that is stored in this memory, the outputs, any of the outputs, regardless of the number of the outputs, is dependent or is calculated based on the current input value and the value that is stored, in this memory. So this is represented like this. So any output value is basically dependent or a function of the input, the current input value or the current input combination, and the value that is stored here, which is called the state. We call it the state. For simplicity, we call it the state. And specifically, we call it the present state. We call it the present state. The value that is stored now. The value that is stored now. So any of these outputs is not only dependent on the input X, it is also dependent on the present state or the queues. Let's call them the queues, Q1, Q2, Q3, Q4, where every queue is basically 1 bit. So there are some certain number of bits that are stored here. We call them Q1, Q0, Q1, Q2, Q3. And this value, along with the input, along with the current input, is used to calculate the output. So for our example, the counter example, here in this memory, we store the current count value. Let's say we start from 0. So initially we have 0 stored in the memory. So whenever X becomes 1, the output should become 1 because the stored value is 0. And this stored value has to be also changed, right? Because when X becomes 1 after a few, let's say, seconds, then the count value should not stay 0. It has to be changed to 1. So the stored value here, or the state in the memory, has to be changed. And how to change the stored value or the present state, basically this is done by the combinational logic circuit itself. So the combinational logic circuit, or the combinational part of the sequential circuit, takes the input X, the present state, which is the current stored value, to calculate the new output, which is the new count value. And at the same time, it calculates the new state, or the next state. We call it the next state, or I like to call it the value to be stored in this memory. For our counter example, if this is initially 0, the memory is initially 0 and X becomes 1, then the output has to become 1, since the stored value is 0 and the input is 1. And at the same time, the stored value has to be changed after we change the output, has to be changed to 1. So how to calculate this one? Basically, it is calculated using the combinational logic part. So this is very important here. To distinguish between two things: the stored value before, the stored value now, and the stored value after some time, which we call the present state and the next state. So after we use the value that is stored here to calculate the output, we also use it to calculate the new value to be stored here after we output the new value. So in order to make things clear, we call the value that is stored now in the memory present state, or present value. And the value to be stored is called the next value, or the next state. And usually we represent them like this. We say a Q of J, which means any Q of T. Now, when I write T, this implies that this is the present value, the value that is now, that is at this moment, that is stored in the memory at this moment. Now, the next state is the value to be stored in the memory, however, not now, after some time when it is calculated. So we denote it with this T plus 1, which means not plus 1 second or 1 hour or 1 day. It is plus 1, which implies this is the future value. This is the next value. So this is kind of notation. This is kind of notation that Q of T implies now, the present value, the value that we have now. A Q of T plus 1 implies the value to be stored, the value that we will have after some time. And what is this time? We will see later. Is it 1 second? It is 2 seconds? It is 1 millisecond? We don't care. It is the next value. It is the next state, like this. So this is a sequential logic circuit. Combinational part, memory, and all that stuff we discussed. The output and next state are function of the current input and state. So the output is function of X and the present state, which is the external input and the present state. And at the same time, the next state, the value to be stored in the memory, is also function of present state and X. So both the output and next state are function of the present state and inputs. And how are these outputs and next state values calculated? Basically using the combinational logic part. So you will see later that when you want to design a sequential logic circuit, you should know how combinational logic circuits are designed. If you don't know how to design a combinational logic circuit, you can't design a sequential logic circuit, because the only difference between the two is the memory, the existence of the memory. And you will see that we will treat the value that is stored in this memory as additional input to our combinational logic circuit. So the whole idea of designing sequential logic circuits becomes combinational logic circuit that has these inputs, which are the inputs, external inputs and the present state, and the outputs and the next states as the output of the combinational logic circuit. So at the beginning, you will find it hard to understand, but if you keep up with me, you will see that it's not that big deal. at the end of the day, sequential logic circuits are combinational logic circuits with memory, and the value of this that is stored in this memory is basically used as additional input to the combinational logic circuit to calculate the output, and at the same time to calculate another set of output or outputs, which is called the next state, which is the value to be stored in the memory. Now, so this is the sequential concept. However, as we said, we can have either asynchronous sequential circuit or synchronous. Asynchronous, what does it mean? What does asynchronous mean? Asynchronous implies that it is not tied to something else. It is not operates in parallel to something else or in sync with something else. It is not tied to something else, which means the behavior of the circuit is independent of time, let's say, is independent of time. So the stored value is allowed to change at any instant of time. So whenever the input changes, the output will change based on the input value and the stored value. As soon as the input changes, the output and the next state technically will change as soon as the input changes. So the circuit does not wait a long time, or does not wait certain event to occur at certain instant of time in order to change its output and next state. So if the circuit behaves like this, where the stored value is only allowed to change is allowed to change at any time, we call the circuit asynchronous. It's the behavior or the operation of the circuit is not controlled by time, is not synchronized with some events, is not synchronized with some events or is not synchronized with time. In other words, as soon as the input changes, this change along with the present state value will be used to change the output and the next state. The circuit will not wait, except for theoretically. However, practically, there is some delay for the inputs to go from here to here. There is some delay. However, the change is not, you cannot forbid the input from changing the output. As soon as the input change, the output is allowed to change. So this circuits, this is one type of sequential logic circuits, which are circuits that contain combinational and memory components. They allow the stored value to change as soon as the input it changes. So they are fast. They are fast. They don't need to wait for anything. As soon as the input change, the output and the stored value are changed. However, they are complex to design. They are not easy to design. In order to design a counter, the counter that we discussed before, based on the asynchronous convention, it will be hard to design when compared to using the other type of sequential logic circuits. Okay, any question? So this is just an introduction, and I always spend significant time on it because I want you to get the idea. If you get the idea, you will see it is straightforward. Nothing is new. This is the introduction part of this chapter is basically what you need to understand in order to proceed for the rest of the chapter. Okay, so this is the asynchronous sequential circuit, and as I said, we will not go into details of this type of sequential circuits because they are kind of advanced circuits. Despite their advantage of being fast, of their ability to change the output as soon as the input changes, they are hard to work with. So they are usually left to advanced courses. The other type of sequential logic circuits is the synchronous. So basically, we are talking about a sequential logic circuit. So there is a combinational component with certain number of inputs, certain number of outputs. However, this is a sequential circuit. So there is a memory. There is some storage circuit, a circuit that can store 1 bit, 2 bits, 3 bits. It depends how many bits that the circuit uses and needs. And the value stored in this memory is, which is called the present value or the present state. The Q of t is used along with the input to calculate not only the output, but also the next state, the value to be stored in this memory, or a Q of t plus 1. So similar to the asynchronous sequential circuit, nothing new. Any output y sub L is basically a function of the present state that is stored, the value that's stored in the memory, and the external input. However, what is the difference? So this is exactly the same as the asynchronous type. What is the difference between this type and the synchronous? The asynchronous basically is when the stored value is allowed to change, when we can change the stored value. This is the main difference. In the asynchronous circuit, we said that the stored value is allowed to change at any time, or basically, what will change the stored value? The change in the input. So in other words, as soon as the input changes, the stored value is allowed to change. The stored value is allowed to change. In the synchronous type, the stored value is not allowed to change at any time. Is not allowed to change as soon as the input changes. The stored value is only allowed to change at specific instant of time, at one time only, at one instant of time. So even if the input changes and that instant of time has not arrived yet, the stored value will not change. So the next state will not be stored here until some instant of time has arrived. For example, let's say the stored value, you can set your system or you can design your circuit such that the stored value only it changes at the top of the hour. Like at the beginning of each hour, you can change the stored value if the input has changed at that instant of time. Otherwise, if you have not reached the top of the hour, if the input changes millions of times, the stored value will not change until 12 a.m. has arrived, until 1 a.m. has arrived, until 2 a.m. has arrived. Any change in between for the input will not affect the stored value. So this is very important, which makes the difference between, which puts the difference between the asynchronous and the synchronous sequential circuit, which is basically the synchronization with time or the synchronization with events. Is the stored value synchronized, or the change in the stored value synchronized with some event, or with synchronized with some time or some instant of time, or not? If it is not, then it is an asynchronous circuit. The change in the stored value can happen at any instant of time. Otherwise, if the change in the stored value can occur at specific instant of time, then it is the behavior of the circuit is synced or is synchronized with some event or with time. Now, these circuits are easier to design when compared to with the design of the asynchronous logic circuits. However, they are slower in operation. Why they are slower? If you look how both types work, you can see it. The asynchronous type can change the stored value as soon as the input changes. So it responds to the change in the input almost immediately or almost in 0 time. So they are very fast. However, for the synchronous circuits, whenever the input changes, this change cannot be reflected on the stored value until that specific instant of time has arrived. So the circuit has to wait all that time before it can change or reflect the change of the input on the stored value. That's why they are slower in operation. They cannot capture the change of the input and reflect it on the stored value unless that instant of time has arrived. All right, so this is the type of the circuits or sequential circuits that we are interested in this chapter. That's why the title of the chapter, if you go back to the beginning, is Synchronous Sequential Logic or Synchronous Sequential Circuits. We will focus on synchronous circuits only. And that's why later you will hear me saying sequential circuits, design a sequential circuit. So is this asynchronous or asynchronous? By default, it is synchronous because we will not discuss the asynchronous. So if I ask you to design a sequential circuit, then by default, it is a synchronous sequential circuit that basically is allowed to change the stored value at specific instant of time. Now the question is how to know this time, how to know this specific instant of time. Basically, usually this relies on the type of the storage that is used in the circuit. So for the synchronous sequential circuit, the memory that we will use is basically has another input that is called the clock. If you want the behavior or the operation of your circuit to be connected with time, then you need some clock in order to measure time, in order to know whether your specific instant of time has arrived or not. So usually the storage elements that are used with synchronous sequential circuits require an additional input, which we call the clock, or sometimes we call it the trigger, we call it the enable, which enables the next state to be stored in the memory. So basically, there is another input for the storage elements that are used in the synchronous sequential circuit in order to connect, to synchronize the behavior of the circuit with time. And this circuit or this input basically is not, it represents time. It has something to do with time. It is it reflects something about time, and usually it is it has this form. It is a clock, which is a function like this. Usually it doesn't have to be like this. Or periodic. This is a periodic. It is usually periodic like this. So this is the shape of the clock. So when you hear that your computer clock is 1 gigahertz or 3 gigahertz, so it is something like this. This is the shape of the computer clock that you use, or your cell phone. The CPU in your cell phone has a clock, and usually it has this form, or it has this shape. So if I say, if I want to use this function or this, we engineers like the word signal to talk about functions. So we call this a signal. So this is the clock signal or the clock function, the clock signal or the clock function. If I want to use this function or this signal to store some value or to define the moment at which I want to change the stored value, what events can I have in this function in order to use to change the stored value? What events or distinguishing events that you have in such signal or that such function? ايش المميز بهاي الفانكشن او السيجنال اللي ممكن استخدمه حتى اميز لحظه زمنيه معينه؟
دكتور،
نعم.
في عنا اللي هو الفيرتيكال لاين، هذا اللي طالع لفوق، يعني قبليه يكون السيجنال مثلا فينا نقول 0 وبعديه 1.
Exactly. So let's say this, the value here is 0, the value here is 1, the value here is 0, the value here is 1, and so on. And this is time, basically. This is time. This is time. So this is basically a periodic signal. We call it periodic square wave signal. Here, squares, square wave signal that alternates between 0 and 1. So if I want to define a specific instant of time, technically I have two instants, this instant and this instant, that are clear, that can be well defined. Of course, I can take any instant. For example, I can take this instant of time or this instant of time or this instant of time, but I cannot distinguish this instant from this instant because they look all the same. There is no change in the input value. However, this instant of time and this instant of time are clear, can be easily distinguished because there is a transition from 0 to 1. So I can design my storage element in the synchronous sequential circuit such that it is allowed to change its stored value at this instant or to change its stored value at this instant of time. So whenever I see this instant of time or this instant of time, I can change the stored value. So this is how we can tell the circuit when it is allowed to change the stored value, either at this instant or at this instant. This instant is basically a transition from 0 to 1. So usually it is called rising edge. It is a rising edge. So we say that our circuit is triggered or activated on the rising edge. So whenever there is a rising edge, the sequential circuit will look at the input at this instant of time and the present state at this instant of time and does some calculation and reflect that on the output and the next state. Or we can design our storage such that whenever we see this event, which is a transition from high to low, from 1 to 0, which is called the falling edge, then we can design our storage element to be enabled, let's say, or to be activated to take or store the next state or store the new value. So usually the storage elements that we use in synchronous sequential circuit are controlled by a signal like this, by a function or an input like this, such that the stored value is allowed to change at this instant or at this instant, at the rising edge or at the falling edge. Or sometimes we call this the positive edge or the negative edge. You can see the board, right? شايفينه. Okay. Okay. So this is the distinguishing factor, which is using the clock for the storage elements. Using the clock for the storage elements in the synchronous sequential circuits. Okay. Any question? Okay, so next time we will go through the storage elements. So in order to build a sequential circuit, whether it is a synchronous sequential circuit or an asynchronous sequential circuit, we need memory or we need storage or we need storage elements or storage circuits. Okay, so next time we'll go into details, and next time is very important lecture, because if you don't understand the storage elements and the difference between different types of storage elements and how different storage elements work, you will not be able to understand the rest of the chapter. The rest of the chapter after the storage elements is basically combinational logic. All what we learned from chapter 2, 3, 4, we will use in chapter 5, but after we discuss the storage elements, because this is the new thing in the chapter. This is the new thing that defines, this is the thing that defines the sequential logic circuits. So please make sure to attend next lecture or see the video when it is uploaded if you can't come to the lecture. It's a very important lecture. Okay? Any question? All right.